Hello everyone, this is Sudha Shrikant. In this video, I have taken up a typical problem of finding out equivalent resistance. Equivalent resistance between a pair of terminals normally can be found by deactivating the various sources and looking into the network within the pair of terminals given or within the terminals under consideration. Now, this network typically has a dependent source. If we can see this network, this has a dependent source. What is the magnitude of the dependent source and what is the type of dependent source we will try to identify. Okay, so strictly speaking, this network doesn't have an independent source, right? There is no independent source. So without independent source, there is no circulation of current in the circuit, right? So there won't be any current, there won't be any voltages. There is no potential differences across any resistances. There are no currents. So because there is no source, okay? So only when you have an independent source, then you will have certain voltages and currents developed across the various elements, and then you may have certain dependent sources in the network. So this Vx by 5, as we can see, is represented by diamond-shaped figure or a rhombus-shaped figure, which goes to say that this is a dependent source. This we have done previously. You can look into the video on dependent sources for better understanding. Okay, what kind of dependent source is this? This dependent source is a voltage-dependent current source. How did I say so? This is a dependent source because of the shape itself, rhombus-shaped. It has an arrow within it pointing downwards. That means it is a current source. If it were a voltage source, we would have had something like this, positive, negative. A diamond-shaped figure with positive, negative inside it. Okay, this has got an arrowhead, which goes to say that this is a current source. The magnitude of this source is Vx divided by 5, where Vx stands for the potential difference across 10 ohm resistor. So whatever potential difference that gets developed across 10 ohm resistor divided by 5 will give me the magnitude of this voltage dependent current source. Now the question is, how will we get Vx? We have to connect a source between A and B. An independent source has to be connected between A and B. Thereby you will get Vx, and that results in Vx by 5 as a voltage dependent current source. This is about the network configuration. But now our problem is we are supposed to find out the equivalent resistance between A and B. So what is the process? This is not an independent source, so that we can deactivate it. So what is the method? There is a simple technique to be adopted. It is a fantastic principle, a very fundamental first principle. If we can appreciate it, it is a very, very simple exercise to do. What we do is, between A and B, we imagine a current source, or we connect a current source actually, right? So we try to connect the current source and try to find out what is the potential difference or the voltage across that current source. Then we infer that whatever is the voltage that is across the current source itself is the equivalent resistance. We come to that conclusion. All right, it is a simple analysis. Let us try to consider this situation. Let us try to I'm justifying how the voltage across the current source itself is the equivalent resistance. See, I have connected a 1 ampere current source. Okay, so what I mean to say is, I will say that there is an equivalent resistance, R equivalent. This is my A and this terminal is my B. Okay, so this terminal A is at a potential VA. And if I can imagine this to be the ground, if I ground that potential, then VA is the potential difference between R equivalent, or in other words, if I want to find out the R equivalent resistance, it is simply VA divided by 1 ampere, voltage divided by current. So VA is equal to R equivalent provided we have 1 ampere current across the R equivalent. This logic we try to make use of, and we try to connect a 1 ampere current source between A and B, then find out the voltage or the potential difference across the current source. the voltage or the potential difference across the current source itself is R equivalent. So this logic we try to make use of, and then we try to find out what is the equivalent resistance. This method is adopted because the network doesn't have any independent source. So we have to bear it in mind. If the network doesn't have an independent source, the method is simple. We try to connect a 1 ampere current source, then try to find out the potential difference. All right. So I will try to ground the B terminal. Okay. So the potential of this node is VA. I will take the potential of this node. I will use a different color perhaps. This is VA. And let me call this to be, let's say, VC. Okay. Let me call that VC because VB is being grounded. I'll call that VC. Okay. I will try to connect a 1 ampere current source here. I will try to connect an independent current source whose magnitude is 1 ampere. I will try to connect this current source to these 2 points. All right. I've connected the current source there. I'll write it properly. A here. Maybe I will remove this B also here. Then I'll put B here. Okay. So now we will try to apply nodal equation. What I have done is this is a 1 ampere current source. All right, this is a network now. Now we have energized this network. That means there is a 1 ampere current source that is 1 ampere is getting pumped via A into this node A. Then there will be current distribution. Then correspondingly, when the current flows through this 10 ohm resistance, there is going to be a potential difference Vx developed across it. And that Vx divided by phi will be the dependent current source that is produced. Now we can work it out. Now how do what's our objective? We need to find out VA. How do we find VA? We apply nodal technique, node voltage method. It's a very simple technique. We will try to adopt. Okay. We will go by first principle. We will not do by inspection because sometimes you may not remember, we may err. We will try to do by first principle. I'll assume a current like this in this branch, a current like this in this branch, a current like this in this branch. And we know that current flows from higher potential to lower potential. So whenever we try to consider the magnitude of current, we need to bear it in mind. Now what do? We will try to write node equation or node voltage equation or nodal equation at node A. At node A. What do we write? So I'll simply write VA minus 0 by 20 is the current. I'll quit 0. Okay, VA minus 20 is the current. This current is VA minus 0 divided by 20. This is the current that is leaving the node. This again is the current that leaves the node. What is the potential difference? VA minus VC divided by 10 is this current. All right, this is leaving. 1 ampere is entering. So we will have that logic. This is plus VA minus VC divided by 10. Both are the currents leaving the node A. This should be equal to 1 ampere which is entering the node. Okay, we will try to simplify this. This results in VA divided by 20 is 0.05 and VA by 20 is 0.1. I suppose this will come to 0.15 VA. Okay, then minus 0.1 VC equal to 1. This is my equation 1. Okay, I'll try to write one more nodal equation at node B. Node equation or nodal equation at node C rather. Node C. Node B is being grounded. Okay, this entire thing is node B. This entire thing is node B. That is being grounded. That is at 0 potential. Now, what is the equation at node C? How do I write? I will take the incoming current. Incoming current to node C is VA minus VC divided by 10. This is equal to VC divided by 5 is one current that is leaving the node C. That is this current we are talking about. VC minus 0 divided by 5. And there is one more current that is leaving, that is Vx by 5. I will take that now. Plus Vx by 5. Okay, so this is another equation we have. How many unknowns are there with us? We don't know what is Va. We don't know what is Vc. Additionally, we don't know what is this Vx. There is one more unknown. So you require one more equation. What is Vx equal to? Vx is the potential difference across 10. It is simply Va minus Vc. He has shown in the problem that this is at a higher potential, this is at a lower potential. So obviously Va minus Vc is Vx. Okay, so we will try to substitute that. We also have Vx equal to Va minus Vc. So we will substitute for Vx in this equation. So what do we get? So we will now get Va by 10 minus Vc by 10 equal to Vc by 5 plus 1 by 5 into Va by 5 minus Vc by 5. Okay, I've simply substituted. I've simply substituted for Vx. So what do I see? Here, if I can see this equation right now, I'm able to see Vc by 5 getting cancelled. Now what do I get? I can simplify this. This comes out to be 0.1 okay, so this is 0.2 and 0.1. I suppose this comes out to be 0.1 Va plus 0.1 Vc equal to 0. I suppose that's okay. This is equation 2. So we have two equations, 1 and 2. We can add the two equations, thereby 0.1 Vc, 0.1 Vc would get cancelled. So we are talking about this one equation. I'll try to enclose it in one rectangle. That's one equation I'm talking about. I'm talking about this equation. Sometimes the rectangle doesn't come out as I intend it to be. Okay, so these two equations are available with me. One equation is in two equations in Va and Vc. So we can solve for Va and Vc. We can add the two. What is it we get? Adding 1 and 2, we can simplify, or simply put simplifying 1 and 2. We can add the 2. Then you will get it to be 1 equal to 0.25. 1 equal to 0.25 V1, rather Va. Thereby, Va equal to 4 volts. Okay? So I suppose we are done. We are able to find out what is Va equal to. Okay, so we are able to find out what is the potential difference across the current source now. This is 4 volts. Now my problem is over. I need not have to evaluate the other voltage Vc. What are we interested in knowing? We are interested in knowing the potential difference here. The potential difference across the current source is simply Va. Okay, so thereby our equivalent resistance is therefore equivalent resistance between A and B. The equivalent resistance between A and B I skipped A, is it? Between A and B is equal to, let me put it this way in words, is equal to the voltage across the current source. which is equal to 4 volts. Hence, I'll use color, RAB is equal to 4 ohms. Okay, this is how we finish the problem. So the equivalent resistance between A and B is nothing but the voltage across the current source, and that comes out to be 4 volts. So voltage is 4 volts, but the resistance is 4 ohms. I suppose that is clear. As I told you, it is simply having 1 ampere current source, and we have this resistance. This is written as RAB, and if I am able to see that this is 4 volt, so obviously resistance equal to voltage divided by current. So that is voltage is 4 volt divided by 1 ampere. This is 4 ohms. This is the logic. This is the logic. We try to find out the potential difference across the current source, and we try to say that the potential difference across the current source itself is the equivalent resistance between A and B. And this method is typically adopted when the network doesn't have an independent source. So we try to imagine, or we try to connect an independent source so that the dependent source gets meaning. Otherwise, it doesn't get any meaning at all, because we know that it is dependent on some other voltage or current in some part of the circuit. So the voltage of the current in any other part of the circuit depends on the energy source. So when you don't have an independent source, there is no dependent source. So this is the technique that is adopted. So simply, if the network doesn't have an independent source, what we imagine is we try to connect 1 ampere current source, try to find out the potential difference across the current source, and we try to find out the equivalent resistance. This is one important method which is helpful in solving problems on theorems also. Okay, I suppose I'll stop this video now. Let me take up few more problems on the other kinds of variations in network analysis. See you in the next video. Thanks for watching.